So the second video for section 5 talks about something called differentials, very closely related to linearization, but instead of estimating the y value, we're going to estimate the change that has happened in y. So just to get us started, I'm going to go through a couple simple examples here. So I want you to imagine a line has a slope of 1/2, and I know that when x equals 3, the y value is going to be 4. And so my question here is, let's say that I changed the x value a little bit. So maybe I went over here and said this is an x value of 7. I want to be able to fill in the coordinates right there, and in the end figure out if I change x, what's the change in y going to be. So if I look at this compared to this, I want to know that difference right there. So there's a couple ways that I could do it. Probably the one that we might think of right now is, let's find an equation for the line. I know a point, I know the slope, and so we just say y equals 1/2. From there we go x minus 3 plus the y value, so plus 4. Okay, so we just keep it in point slope form. Okay, hopefully that makes sense. And then from there, if I wanted to, I could say, let's plug in the 7 into this function right there, figure out what the y value is. So if I put a 7 in there, 7 minus 3 is 4, 4 times 1/2 is 2, 2 plus 4 is 6. So the coordinates here would be 7, 6, and again, if I'm looking for the difference in y, the change in y compared to, whenever this happened, okay, so we had a change in 4 for x, the change in y would be 2. 6 minus 4 is 2. But is there another way to think about this? And I'm going to argue that maybe there is. Okay, if I were to think of the slope, okay, our slope for this is 1/2. Okay, and our change in x from here to here is 4. What's 1/2 times 4? We get 2. Just like the difference between our y values. Okay, let's try to look at another example, see if the pattern holds up. So for our next one, we'll say that we have a line slope of 3. It's going to go through 2, 4, and I want to know what's going to happen. Let's say this time we're going to move over to 6. Okay, if I go from 2 to 6, a change in x of a value of 4, what's the change in y going to be? So again, if I go up here, okay, maybe I have to extend this a little bit, but what's the difference in those two y values? What is this going to be when I change x this much? Okay, so maybe I'll put in a few more labels here. If we go up above to our previous example, this was maybe our change in x, so dx. This is going to be dy. This will be dy. We're trying to find the dy's, and we know the change in x. Okay, so again, we could go through, we can make an equation of a line. I could say that for this one, y equals the slope of 3, and I'd have x minus 2 plus 4, and I want to figure out the coordinates for this next point. So I would plug in a 6 now. 6 minus 2 is 4. 4 times 3 is 12. 12 plus 4 is 16. So over here I'd have 6, 16. And my change in y, my dy, is going to be 12. Okay, is there another way to figure that out? Sure. Again, I take the slope of my line, which is 3. I look at the change that happened with x. So from 2 to 6, I have a change of 4. 3 times 4 equals 12. I get the same number. So what I'm trying to argue here is that if we're looking at this, and I'm kind of basing it on a fixed point, okay, the change in y, what's going to happen with y, will equal my slope times the change in x. Okay, now let's try to take this to more of a calculus sort of idea here. So now instead of a line, we have a curve. Okay, so let's say this is function f or function g or function h, whatever. Okay, but I'm going to base it on this x value. Okay, and then I'm going to get a point from there. And so the y value would kind of match up right there. Okay, what's going to happen then? I'm going to change the x value that I'm interested in. I'm going to go to the right a little bit. somewhere over here. Okay, and then if I match up that point to the function, I'm going to get something there. And match it up with that y value there. So the general question here is, as I have a little change in x, can I figure out what the change in y is? Well, if I know the actual function, I could just plug in that x value here, get the y value, do the same thing here, and then just subtract one from the other. But that can take a little bit of work. So is there a calculus way that will give me an approximation of this? And so again, we're going to go back and think of a tangent line. So let's draw a tangent line into our picture here. Okay, there's our tangent line. And now, if I were to think through this a little bit more and relate it to some of the pictures from before, if I match up the same point right here on my tangent line, I'm going to get something right there. Bring it over, it's going to be something about right there. And I can use the same method that I did on the previous examples to get this distance. Okay, even though I want this, because I really want to relate it to the original function, I want to know that, I can actually get some sort of an estimation by finding this. And when my change in x is really, really small, these differences won't look quite so big, right? There's a pretty big gap there. This is half of what this is. But when my change in x is really, really small, when it's really right around there, these two values will be almost the same. So what did we do on the previous slide? Okay, we said that to find dy, we would take the slope times the change in x. So what I'm saying here is that this part of my picture is the dx, that can stay the same. This part is dy, it's not the exact change now, it's more of an estimated change based on the curve function, the curve function here. But how would I recognize, or how would I think about the slope? So we were talking about the slope of a line, but now we can say the slope of the line at this point is just our derivative. And so for a differential, the formula that we're going to use is dy, the change that's going to happen in y, it's an estimated change, is going to equal f prime of x times the change in x. And that's what we're going to use anytime we see a differential question. That's kind of a simple, maybe it didn't seem simple to you, but a simple sort of proof. If we wanted to go through a very technical proof, it'd probably take me 15 minutes to walk through, but hopefully that kind of convinces you that this is a formula that we actually can use. So our question here, find the differential dy when dx is 0.01 and we know that x equals 2 if we have this function here. And then we need to explain what we found. So remember, for this, we're going to be saying that dy equals f prime of x times dx. So first thing, we need to find a derivative. Okay, I know that from this we could say that I'm going to say that this is really like f of x, the function that we're dealing with. So f prime of x would equal 5x to the fourth minus 12x squared. And I'm interested in what's going to happen when f is 2. So f prime of 2 would equal 5 times 2 to the fourth minus 12 times 2 squared. 2 to the fourth is 16. 16 times 5 is 80. 2 squared is 4. That would give me 48. So in the end I would have 32 as my answer for the derivative at 2. So going back up to the top, way up here, remember this is what we're going to look for. Really what this formula would be saying is instead of f prime of x, we're going to be looking at f prime of 2. But from there, f prime of 2 we found out was 32. Okay, the dx they tell us is 0.01. And so that would get us an answer of 0.32. Okay, so now we get our answer. What does it mean? Well, there's probably really two ways that we could summarize it. I'm going to pause it a second and just write stuff out and then show you what I wrote, try to explain it. But a couple ways to interpret this. Okay, so here's the summary. We would start both cases by saying when x changes from 2 to 2.01. Okay, that's what we're saying up here in the instructions. X is 2, we're changing it by 0.01. It's going 0.01 to the right. Okay, we could either say, number one, probably the most common one, y is going to increase by about, it's an estimation, by about 0.32. That's what we're really finding up there. Or we could say that y is approximately, the actual y value is approximately 0 plus 0.32. Okay, so where did this 0 come from? Well, if we go back up to the original function, if I were to figure out what f of 2 is, remember that's where we started, right? If I were to plug a 2 into the original function up here, right, 2 to the 5th minus 4x cubed, or 2 cubed, I'm going to end up with a big whopping 0. So we'll go back down here. I'm going from 2 to this. So I'm going to start with my value at 2, which was 0, and I'm adding about 0.32. Y is changing by about 0.32, so we still get the same answer as above, but they mean different things. So one is here we're kind of saying here's how y is changing. Here we're saying what y is approximately the actual y value, and we need to make sure we understand where that 0 is coming from. Okay, jot down some questions. See you tomorrow.